All right, I think we are live. Thank you for joining in, everyone. Arnav, Raghav, Muskan is here. Um, Today, we are here to hear from Raghav and Arnav, of course. They have worked on a very interesting project related to optimization and robotic surgery. This is part of the school research program at Chinta, and I do apologize. The electricity in my area is coming and going, but I think now it's back. So Arnav and Raghav are both in schools. So Arnav is from Delhi, who's in grade 10, and Raghav is from Bengaluru. He's in grade 9. And we also have two of the fantastic research associates. We have Muskan, who has worked with the kids. Sharif is also there, of course. Sharif has also worked with the kids. So I'm really excited to hear from Arnav and Raghav. So the way this works is that you just tell me to go to the next slide, and I will just go to the next slide once you're done with the slide. Okay. And okay, so I'll just go to the first slide and let's get started. So who wants to pick it up? Is it Raghav or Arnav?
I'll pick it up, sir.
Okay, that's great. So go ahead, Arnav. Let's start.
Good evening, everyone. Today, me and Raghav are going to present on the topic enhancing optimization and accuracy in robotic surgery through advanced geometric techniques and innovative algorithms.
Is there a problem, Arnav?
No, sir, it's fine.
Okay.
Next slide, please, sir.
Okay.
So, data augmentation. So, next slide. So, in this method, we artificially expand the amount of training data we have by making small changes to the original data. This helps us to improve the model's ability to generalize it by exposing it to more variety. For example, in the example shown below, we have rotated, flipped, or blurred the image of the cat. Sir, my mic is being mute.
Oh, I'm sorry. I'm by mistakenly I'm muting your mic. When I'm
Uh,
trying to mute my mic. Sorry. Yeah, please continue. Yeah, yeah. Please, sorry.
so these changes create new, slightly altered versions of the original image, which helps the model learn better without actually collecting more real data because it is limited. This is also termed as adding noise. So next slide. Underfitting is a challenge we encounter in data augmentation that happens when the model is too simple to capture the patterns in the data which we require, leading to poor performance on both the training set and the new unseen data. It means that the model hasn't learned enough from the data. So here, what we refer as performance is how well a model makes predictions or classifications on a dataset. Now, overfitting. It is just like rote learning for a model. It memorizes the training data, including noise and specific details, which makes it perform very well on the training data, but poorly on new unseen data because it can't generalize what uh, beyond it has memorized. And the ideal model is the perfect desired model that infers the underlying patterns without also fitting noise.
Next, I'll be talking about the beautiful world of neural networks. So, neural networks is a really cool thing that is inspired from biology. So, in our brain, we take decisions in our daily lives. We do whatever we do is based on various neural network layers, the synapses of our brain that causes to and leads us to perform any decision or do any action, and this is where neural networks comes in. So this integrated with AI and ML creates a deep learning model that can easily identify the complex patterns and make database predictions. It mimics the neurons in the human brain. So, next slide, sir. So, I'll tell you how it works now. So, let's take an example of a model that is being trained to recognize numbers 0 to 9. So, let's have an input image of 9. So, let's divide it into 28 cross 28 pixels. So, now each pixel can have a corresponding threshold value from 0 to 1. 0 for black, 1 for white. And the middle variances for like gray, dark gray, etc. Now, 28 into 28, 784, I can arrange all of these pixels in a 1D dimension, as you can see in the input layer of the neural network. Now, each one of the pixel can correspond to new neurons and thus creating some hidden layers. These hidden layers are nothing but the kind of procedure we are following for identification. For example, let's say our procedure can be like identifying how many lines and curves are there in the number. So I've created two layers over here, just for example, one for detecting the lines and one for detecting the curves. Then the last output layer will all of the neurons map to is where the real fun part comes in. Because in this layer, the highest threshold will be the one which is our output or the number detected. So now I'll go a bit deeper on this. So next slide. So first, we assign some weights and biases to each and every neuron. Maybe lines have more, if there are 5 lines, for example, but the detection for corners or curved corners is not that good. So maybe I can add some strength to the lines. Maybe there is some parameter that has more weightage than the other. So that's where the weightage or WI weight comes from each and every neuron XI. Then each and every corresponding neuron can have its own inhabited bias. So this can be regulated for again for having that weightage between the connections. Then this will result in some huge number, maybe more than one, like 10 or maybe 60 according to our neurons. But that will cause but according to our neurons, that can already only take the values from 0 to 1. That is not possible. Hence, we apply the sigmoid function in the last. This sigma function, the small sigma notation function, this just like squishes all the values in between 0 and 1 range. So, sir, next slide, please. So as you can see, the sigmoid function, I've put a graph of the sigmoid function too, as each and every value can correspond to a different value in the range of 0 to 1. So it's like a squishing function that squishes all the values in the range of 0 to 1. Next, sir.
So, just like humans, we try to mimic how they identify their mistakes. Just like reverse engineering, we try to match the predicted and the required output, and then depending on the variation, we adjust the weights and biases, which Raghav talked about. This is back propagation. So, next slide. K-fold cross validation. To keep overfitting in check, we use k-fold cross-validation. What we do is that we take the data, divide it into k equal parts, then the model is trained on k minus 1 folds and then tested on the remaining one. This process is repeated k times with each fold once being used as test set. To combine the findings, we average out the results. So next slide. Now, robotic surgery and precision. For the movement part of the robot, we build a map on it for it to follow on the coordinate system. Next slide. So these are the coordinates we assume. Now, as the picture is 2D, we can observe the x and y coordinates easily. But the main problem is the z coordinate, which we find out using stereo vision. So the z coordinate is given by f into b by d, where f is the focal length of the cameras, b is the baseline distance between the cameras, and d is the difference between the images we obtain. Now Raghav will explain why we take these into consideration.
So for this stereo vision, how does this work? What is baseline? What is disparity? It's okay. So the thing is, we have two cameras placed adjacent to each other. So by this, sir, if is it possible that I can annotate, or I think sir you're muted.
Okay, sorry. You want to manage the slide?
Like, is it possible to annotate?
Oh,
Like
no,
on
no. I don't think it's possible to annotate. No, sorry.
Never mind. I'll just explain like this. So,
Mhm.
stereo vision. So, we can have two cameras placed next to each other. So, if you can hold out a finger in front of you, you will and see the finger from your left eye, you will notice and then change the eye which you view from to the right eye. You will notice that your finger changes the position, right? That is the parallax effect. So, the farther away my finger is, the lesser is the disparity or the parallax effect, and the closer it is, the I can see the movement of the finger more large and apparent. Thus, I can from this I can get to know about the z or the depth of the object from the camera. So we have two cameras placed next to each other, and then we'll compare all the images taken by both of these cameras, and then the disparity, which is the distance traveled by a specific object. This can be said as the disparity or the distance, and then obviously this is, as I told you, it is inversely proportional to the z coordinate, hence it's in the denominator, with the baseline, which is the distance between these two cameras, to the focal length of the cameras. So this extracts the z coordinate. I hope that is all clear.
After that, we infer the angular coordinates. As you can see in the picture of the aeroplane model, theta, phi, and psi are the Euler angles that are used to understand any rotation. Psi is the angle sidewards, theta vertically, and phi sideways. Now, the angles we derive from 2D images can be calculated as shown, where u0, v0 are the image center coordinates. These refer to the specific pixel location in an image that is considered the center of that image, and fx and fy are the focal lengths in x and y direction.
Now you would ask, why do we need the angular coordinates when we already know the Euclidean most common x comma y comma z coordinates? Well, our robot isn't not just moving from a point to a b point. We also need to know about its orientation at that particular point. So that orientation can be easily calculated by the angular coordinates. I would like to say this as a six coordinate system: x comma y comma z comma alpha comma beta comma gamma, which x comma y comma z are the Euclidean distance coordinates and the angular coordinates alpha beta gamma. This can be referred to as a state of a of the robotic arm at a particular position, a state, an orientation, and the coordinates, a state. So this state to that state. So the robot can easily maneuver from one state to another state. That leads us to the second slide. Sir, can we move on to the second slide? Yeah. So we can easily find the Euclidean distance by the most very famous formula of square root of x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. This is giving us the distance between 2 points in the Euclidean xyz plane, and the angular distance, which is just the distance between orientations, you can say. Combining both of them, zero point 0.5 of the Euclidean distance plus zero point 0.5 of the angular distance, help us accurately change the robot from one state to another, having precise movements from one state to another. There's one more technique that can be used to, after you know the distance, you can apply this technique to have a refined movement. So, next slide, please. So this technique is of iterative approach to refine movement. So in this, we follow a recursive approach. So first, you calculate the distance. Obviously, first you identify the current position and the target and measure the distance. Then move half of the distance. Then if there's some error metric, you move the error metric, which is just the actual position minus the desired position, and then you again measure the distance remaining, then you cover half of its distance, and so on. So it's like reducing steps exponentially. Sir, can we move on to the next slide? So the robotic arms moves in steps that reduce exponentially, that leads in a more refined and accurate movements. So that there, if there are some errors or some deflections in the movement, there is, we can easily huddle overcome over these hurdles and then have a most refined and accurate movements as desired in very complex surgeries. The next slide.
The potential of machine learning in robotic surgery. So, machine learning can greatly improve robotic surgery by making it more accurate and helping robots make better decisions during operations. By learning from past surgeries, these robots provide safer and more effective treatments for patients. Convolutional neural network (CNN). It is a type of neural network designed to recognize patterns in images by breaking them down into smaller features. It processes image through multiple layers, allowing it to identify faces or animals with high accuracy. Also, let's explore a basic CNN model using TensorFlow and incorporate the concept of cross validation, which efficiently detects brain tumors with an average accuracy of 72.6%. Brain tumor detection. So, brain tumors can either be harmless or harmful. Finding them early is the key to getting the right treatment and improving the recovery chances. Deep learning is now a strong tool to sort medical images. This technology uses techniques like cross validation and data augmentation to improve its accuracy and reliability. The dataset consists of brain tumor images in two classes. Yes, for if the tumor is present, and no if it is absent. Since the dataset has two outcomes, it is trivial that we have used the binary system with 1 for tumor presence and 0 for absence. The model is trained for 20 epochs, recording validation accuracy for each fold. It helps in the constant improvement of the model by adjusting the techniques. Epoch refers to one complete cycle through the entire training dataset when training a model. Now, the final model is a culmination of how data augmentation, group theory, distance metrics, CNN, and k-fold cross-validation work together. Future work could explore transfer learning with pre-trained models like VGG16 or ResNet to enhance accuracy.
Coming to the results. So how can we evaluate the model? How can we get to know how its accuracy is, how it's performing? Well, that's where the confusion matrix comes in. Confusion matrix is just a 2 cross 2 matrix that represents some four values, which I'll be telling right now. So next slide, if possible. So 13, 6, 3, and 15, I'll just put them in that order. So 13, the top left one, represents the true positives. So Arna will be saying what is the positives and negatives and true and false.
So we can break this down for understanding. Like true false tells us if the prediction is correct or incorrect, and positive negative tells us the prediction made.
Yeah. So positive, like if you remember, like any report, any medical report, if you're diagnosed with a disease, you get a positive, means that you are diagnosed with the disease or you have brain tumor in this case. Negatives meaning you do not have brain tumor or you are not diagnosed by it. So, and true false, saying whether model truly correctly identified brain tumor, while false positive is the case where the model could not gave a positive report, which means it gives a false alarm for having a brain tumor. False negatives is just negative that is false, meaning the person actually had brain tumor, but the robot or the model said that you don't have a brain tumor. True negatives is when you actually correctly predict when actually the brain tumor wasn't there. Now, if you would notice, the false positive is greater than the false negatives, which is quite necessary. We don't want anyone running away from the hospital saying that I don't have brain tumor, and when the person actually has brain tumor, that's worse than the scenario in which the person does not have brain tumor, but we are predicting it you have a brain tumor, because in this case it's like just a precaution or maybe just an alert for the person for brain tumor, and it doesn't cause any harm. So thus the model is trained like this. You might think that the incorrect predictions are quite less, and I'll be moving on to the. Comment on this afterwards. So next slide, yeah. So accuracy. So accuracy is just we have a very simple formula for accuracy: true positive plus true negative upon true positive plus true negative plus false positive plus false negative. So by this, we get the accuracy of the model to be 75%, which is quite reasonable. So next slide. Which is quite reasonable for now because we used so many complex techniques such as CNN, K-fold cross-validation, data augmentation, and at such a small data set of just 100 images, and still it has given us a value of 0.76 with compared to a basic model without all of these techniques of 0.68 or 68%. Well, you might say the difference is quite less, but I feel it's quite reasonable for now because we have added such complex techniques on a very small data set, which is quite not desired and can lead to overfitting. So thus you can't see that difference. But I'm sure that this technology can also will lead into maybe one in a million incorrect prediction in the future with the large data set and with experience. And that's what we are coming to the next, the future prediction, the future technologies and the future developments that can be made in this field.
So there are some methods that can be applied in the future for the further progress of this field. Biomechanical modeling. It mimics human tissue behavior so that the robots know in real time what the human is sensing. The other one is AI powered real time decision support systems. They use advanced algorithms to analyze data instantly, providing timely insights and recommendations to help the robots make informed decisions quickly and effectively.
And
Now,
one thing that I really like, sorry, Arnav,
no, no.
one thing that I really like about what when we discovered about like we were researching about biomechanical modeling and AI powered real time decision support systems. When Arnav came to me with this idea, we were like so intrigued by it because now we could know that robotic surgery isn't just where a robot is just hard coded to do something. It might have some feelings now. It might now start having it's like a feedback system with it, so that it can understand how each and every move is having an outcome on the patient body, and it can acclimatize to the changes that are occurring in the surroundings, and that is quite awesome according to us.
Actually, I'm a sports enthusiast, so these technologies are used a lot in them. The first two. Now, to execute a surgery, a robust plan is needed. And the predictive analytics for surgical planning uses machine learning to forecast potential problems and improve the plans before surgery, helping doctors prepare better for what might happen during the operation. Now, nano robotic surgery. For a minute level operation where space is limited and it may be performed internally also. Nanorobots can be used. It has a very large scope. These advancements promise to transform surgical practices, making them safer, more efficient, and personalized.
So, in conclusion, I would like to say that the future of robotic surgery is at large scale. It's like it has great potential to transform healthcare. These innovations and AI decision support, predictive analysis, autonomous robots, adaptive learning, AI, deep learning, and new techniques that are coming in to improve the accuracy and precision. It's just not a new technique that can just be used now. It's in fact just starting to multiple new techniques that can be grow out of all of these techniques, leading to a more transforming the healthcare, making more efficient. And one more thing that I like about this is, since man labor costs can be more than the actual robotic costs sometimes, with this technology can even go to the underprivileged, and where the in the rural areas where the health facilities aren't there, governments can put all of these robotic machinery over these places, which can might replace uh, doctors who are in those places, leaving the complex tasks to the doctors to decide. This really is a great potential for the future, and I hope we have showed you about its great potential. We have even explained the quite a small model which we students small students made with just 76% accuracy. Imagine how great the accuracy level will be when amazing scientists all over the world make it. So it has great potential and we remain amazed by it. Thank you.
Thank you.
Excellent, very nice, very nice. I mean, this is I really love the the presentation, the way both of you did it together. It
Thank you
was
so
like
much.
very well. It seems that you've prepared really well. And also, one of the things that I always tell students in school is that school research is about asking the questions and learning about something that you may not have learned before in school. So clearly, both of you have done that, which is fantastic. We can also think about follow up on this. Like one of the things that you may look into is how to apply robotic surgery in plant phenotyping. I mean, there is, I mean, you don't have to experiment with humans. I mean, you are not allowed to do that, obviously. But we can obviously build something and that can work on plants. Uh,
So, in
yeah,
fact, we researched about this too. I did too, because when we were exploring about our motivation came from the Da Vinci system, which is existing with high levels of accuracy using these geometric techniques and deep learning. This system is newly introduced in the early 2000s, and this robotic surgery equipment is controlled by
A
its main
surgeon.
by the surgeon. It's not fully automated yet. Future plans are there to fully automate it, but right now it's controlled by surgeons, and it had that accuracy that the surgeon could stitch a grape
Hmm.
with the Da Vinci system, and that was mind blowing. level of accuracy and precision.
Excellent, excellent. Fantastic, Raghav. Fantastic, Arnav. Excellent work. Keep on working hard, I would say. I mean, you have like a very long run time, like you are just in grade 9 and 10. So asking questions and learning deep ideas is very, very important. And clearly you are doing it. And I would also thank Shaif and Muskan, the two researchers who actually worked with Arnav and Raghav on these projects, and made all of this possible. We will keep on continue. We will continue to work hard, really hard, and get some more interesting results in future. Okay, thank you. End the presentation here. Again, all the best. Excellent work. Bye.
Thank you so